Okay, so let's get started. Going to turn the camera. All right, so today we'll start a new chapter. As I said, the conceptual portion of the class is all done. We are now going to switch back to more systems level issues, starting with web applications and the World Wide Web today. Next time we'll talk about content delivery networks, some aspects of edge computing, web caching, and then we'll talk about file systems and there's a few more topics before we end. Okay, so today I'm going to start a very high-level description of the web, web protocols and things of that sort. Next time, we will use web caching. Maybe towards the end of the class, I'll start talking about web caching. But really, in the next class, we will use web caching as an example of how to implement some of the consistency ideas we had talked about maybe 2 or 3 classes ago. Okay, so let's talk about web. So this is a picture that you are all familiar with. I've shown this very early on in the class as well, maybe in the first or the second lecture. Okay, so in terms of web applications, okay, the standard one is one where you have a web browser. Okay, it's a human that is trying to browse the web, and then there's a web server. Okay, the browser sends HTTP request to the server, retrieves documents or images or any other type of information from the server, and then displays it at the browser. Okay. Now, not all web systems are browser-based. Okay. You can have web applications that just talk to one another without any human involved. Okay. You've done some of that maybe in your microservices implementation. If you use REST architectures, you have 2 components that were just talking over HTTP. Okay. But for now, let's just assume that our client is a browser and the server is a web server. But keep in mind that you don't actually need a human on the client side. It could just be 2 web services talking to one another and so on. So with that picture, okay, let's just talk about the browser for a second and we'll talk about the server. I had also shown something like this long time ago. Okay, so these are some of the key elements of any browser application. Okay, there's a web user interface. There's the GUI that the web browser is exposing to the end user. Okay, but the main parts of the browser include the browser engine and the rendering engine. The browser engine is the one that is actually responsible for implementing some of the key browser functionality. The rendering engine is the one that, in this case, actually renders the documents that are fetched from the server. Okay? The browser has to communicate with web servers. It can decide whether to use multiple threads. If you have a threaded-based architecture, you can use multiple processes. If you have a process-based architecture, okay, Google Chrome specifically uses a process-based architecture. Each tab that you have in Chrome actually is a separate process. Okay? And within that process, you can have multiple threads that are being used to go fetch elements of whatever web page you're trying to fetch and so on. Okay? So different types of architectures could be used depending on what type of browser it is. Okay? And here's an example of a web server. Okay, here I've shown the Apache web server, which is a very popular open source web server that's widely used for all kinds of web sites or web servers. Okay, so you will see that it uses a modular architecture and more of a pipeline processing model. Okay, you will see that there are a set of stages and the requests that are coming to the server get processed through these stages. Okay? Now, as far as the architecture of Apache is concerned, okay, it actually supports both a processor pool model as well as a thread pool model. You already know what thread pools mean, right? And when I was talking about some of this, remember I also said you can have a set of processes that are doing the same thing. You have a master process, it receives requests, it again hands this request to one of the child processes, and you can have a set of processes that are part of the process pool. So you can actually configure Apache in either of these 2 ways. Okay, the standard Apache model actually uses a processor pool model. Okay, does not use a multi-threaded server like you have maybe implemented in your lab, it uses a multi-process server. Okay, and then you can essentially send requests to individual processes and so on. But there are versions of Apache that also can be configured with threads rather than processes. Okay, so it supports both. Okay, and so that's the architecture. But as far as the software implementation is concerned, it's highly modular. Okay, you can have base Apache and extend it with all kinds of modules that give new functionality. Okay, for example, you can implement a PHP module that allows the server to essentially process PHP-based web pages. PHP is a server-side scripting language that you can implement in the server. You can implement security functions on the server by injecting modules and so on. And these modules will sit somewhere in the processing path. Each of these boxes that you see here, you'll see the modules at the top. Each of these boxes are modules, and there are hooks in modules. So when a request comes, it goes to module 1 and module 2 and module 3 and so on until it's processed by all the modules in some sequence, and then a response is generated. Okay? So modular architecture uses process-based but also supports thread-based pools. Okay? That's the thing you want to keep in mind. That's all I'm going to say about Apache, because that's not really the goal of what we want to talk about today. Okay? But before I move on to some other things, I also wanted to talk about proxy servers, because we will come back to this next class and talk about it at quite some length. Okay, remember when I talked about this some time ago, I said a proxy server sits between the client, which is shown here as the browser, and a server, which is shown here as an FTP server. So it sits in between, okay? And it can serve a number of different functions. Okay, for in this figure, it's doing what is called protocol translation. Right? So your server here is an FTP server, so it can only speak FTP. But if you want to expose HTTP functionality for downloading files rather than pure FTP functionality, you can put a proxy in between the client and the server. The proxy is the one receiving HTTP requests. It translates them to equivalent FTP requests. In this case, the only HTTP requests that are going to be served are essentially gets and puts, as we'll see. So you do this protocol translation, and then you get an FTP response. You translate that into an HTTP response and so on. Okay? So you can use proxies to translate between the client and the server if they don't speak the same protocol. That's one example. Okay? Another example is in the context of video streaming, which we'll encounter in a later class, maybe next week. And you can also use it to translate the content. For example, the web server in this case could be serving video content. The video content may be created at, let's say, a certain resolution. Maybe the device is a phone with a lower resolution. Okay? So if you send it higher resolution video, that's not very useful because you're using more bandwidth than is needed, and then anyway you have to shrink it. So the proxy in this case could actually shrink the video on the fly. Is a process called transcoding, and then send the right resolution video to the end client. Okay, so there's another function that the proxy can perform. You can also put a cache at the proxy. Okay, in this case, the proxy is just caching or replicating some content from the server, and then you can just serve that content directly from the cache rather than sending it to the server. Okay, the use case that we are going to look at next class is the caching use case for proxies. But keep in mind that proxies can support many different use cases, not just caching. Okay, you can do protocol translation, you can do transcoding, you can also do caching, and maybe a few other things that may not be relevant to this class. Okay, so that's our client proxy server architecture, which we'll again come back to next time. Right? Okay, so with that in mind, let's get back to our web applications. That's going to be the focus of today's class. This is essentially a multi-tiered architecture. We had seen this, I think, in lecture 3 or 4. Okay, here you see that request. So there are 3 tiers in this case. There is a web server tier. Okay, there is an app tier, which is shown here as a CGI process. Okay, and then there's a database tier. Requests come into the app, to the front end tier, which is HTTP tier. They are sent to the app tier, which might make queries of the database, and responses go back. So requests flow in one direction, responses go in another direction. This you should all be familiar with. This is just a recap of what we had talked about many classes ago. Today we'll talk a little bit about how to generalize this into other architectures like microservices and so on, and also clustered architectures. Okay, so this is a standard three-tier architecture. But if you have large websites, okay, you may actually replicate some of these components. Okay. Here we have an example where you have replicated that entire web server, which means all the three tiers that you have are replicated 4 times, as you see in the top, and as a front-end server sitting in the front of these servers is the receiving request. Okay, so requests come to the front end. Okay, the front end can then decide which of the web servers to send that request to, and then the response goes back. Okay, now the front end server could use any type of mechanism to decide which server to send its request to. You could do simple round robin load balancing as one example. Okay, successive requests that come into the front end could be sent to successive servers. Okay. Now, if your server is stateless, that's a good way to distribute your requests and distribute the load across multiple replicas. Okay. But what if the server was stateful? Okay, the server actually keeps some state on behalf of the client. So, for example, this could be a e-commerce application, an online shopping app. Okay. The user may be browsing an e-commerce site, and they may have put some item in their shopping cart. Okay. The fact that there's an item in the shopping cart is state that is relevant to that particular user or client. That is state that is kept in the memory of one of these replicas. Okay. So if you're doing plain load round robin load balancing, okay, then the next request goes to another replica from that client won't know anything about the state of that user, which is stored on another replica. Okay? So you cannot just do round robin load balancing if you have session state at the server. In this case, you have to do what is called session level load balancing, which means that first time a user makes a request, the front end assigns it to one of the servers, maybe using some round robin techniques or least loaded technique, and all subsequent requests from that user have to be sent to that server. Okay, so that the state can be correctly dealt with. Okay. Otherwise, if you just do round robin, like I talked about, request level round robin, that's not going to work. You have to do session level round. Okay. So all kinds of different policies could be used by the front end server to decide how to load balance across web servers. Okay. Is that clear? Okay. Now there is one subtlety I didn't talk about, which is if you actually replicate all the tiers at each of those boxes labeled web tier, web server, then your database is also getting replicated. Okay. Now that is going to create additional issues where if you actually, let's say, make a transaction and you purchase some item from your e-commerce store, okay, that state of the database will change because you are now maybe adding some entry saying an order was placed, and then maybe you have to change the amount of items in stock and so on. So that is state at the database, in which case you have to now make sure the database replicas are consistent across the various web server replicas. Okay. That's going to impose additional overhead that's not shown here. So one common approach that is used in when you have clustering is to not replicate the database backend. So you'll see that there are multiple tiers here. So one common approach is not replicate the database backend, so get rid of the consistency problem and put the database on a large enough server so that you can handle the load on one machine. Okay? And in that case, you can replicate these other components, okay, but not the database. Okay? That's one approach. Now, if the database server is seeing a heavy load, then you might have to either replicate or partition the database, which brings you back to then you got to make sure the copies are consistent and so on, which imposes additional overhead. So depending on the scenario, you can decide which option makes more sense. Okay? I believe in lab 3, you're not replicating the database backend, but you're replicating the front end application, which simplifies the problem because you don't need to worry about how to keep the databases in sync. But if you had replicated that tier as well, then you have to have additional consistency protocols at the database level also. Is this clear? Okay. So many different issues with regards to what is replicated, or is the backend replicated or not? How do you ensure consistency for the backend and so on? Okay, so that's something to keep in mind as far as web server clusters is concerned. Here's a more detailed picture of how some of this could work in a clustered system Okay, so there's a client here that is sending requests. Everything else here is actually part of the server. Okay, so you will see that the server has something called a switch. That's essentially the front end with a public IP address, which is where all the requests are coming in. Okay, so that's your load balancing switch. It could actually be a hardware switch. If you have really high request rate, okay, the front end can actually be a hardware level switch for additional performance. Okay, but often it's not a specific hardware device. It could just be a regular server that's receiving requests and then doing load balancing in software. But for very high-end servers, that actually is implemented in hardware in the switch, which is why it's called a switch. It sounds like a hardware element. But whatever it is, whether it's a software element or a hardware element, this switch is essentially going to forward, talk to the dispatcher, which is where the load balancing algorithm is sit. Okay, although that's shown as a separate component, the dispatcher algorithm is often running on the switch itself and not on a separate server, but it doesn't have to, which is why it's shown separately. But the more common case is the dispatcher is the one that's doing load balancing. So that's going to be sitting there. It has to decide for every request that comes in where to send that request to. Okay, and this example shows two replicas. Okay, so either you are going to send the request to the top replica or the bottom one. In this example, it goes to the top one, and then the responses go back to the client. Okay, so these architectures can get somewhat complicated because there may be load balancing hardware switches, there's load balancing algorithms, and there are all these replicas. And whether the database is replicated or not is yet another issue that's separate from just replicating the front end. Okay, so all of this is just to say that when you have large web systems, okay, the architecture of these web systems can be complicated. And we haven't even got into microservices. There's lots of different components of that web application itself. This is just a very simple web server or a multi-tiered system, yeah, which is the simplest of all. Yes, question. Okay. Yeah, so that's a good question. The question is, why is the dispatcher sitting separately? Why is it not in front there? And why requests are sent to the distributor and not sent there? So this is showing a little bit older architecture where what happens is the switch is blindly sending the request to one of the web servers. Okay? That web server contacts a load balancing algorithm saying, am I the one to service this request or not? If you're not, then you do what is called a TCP handoff and forward the request there. Okay? Otherwise, you handle it yourself. Yes. Now, a better, cleaner architecture is to put, as I said, put the dispatcher in the switch and avoid all of this problem. Request comes in, the load balancer decides where to send it to, and you send it to the right server to begin with. You don't send it to some random server. That random server distributor talks to the dispatcher, and the dispatcher picks a server, and then if you're the wrong server, forward it. This was actually what was done at one point, but I think the cleaner one is not to do this at all. Put everything in the load balancing switch and have it deal with it. Okay. Yes, question. Yeah. So question is the step 3 where it's doing a handoff of a TCP connection. Is that doing something special? Is the switch have to be involved and so on? Okay. So it turns out that there are actually many different ways to do what is called a TCP handoff, which is what is being done here. In some cases, the switch can actually take the TCP packet, rewrite the IP address, and send it to one of the servers. So the server believes that the request directly came from the client. Okay? Because remember, the client has actually set up a TCP connection to the switch and send a HTTP request over it. Okay? Now, if you want to hand off that TCP connection and this server believes that the connection came to it, you have to do some rewriting. Okay? So that requires you to do some network level tricks for the server, web server, to believe the request directly came from it. And the reason you do this, okay, is if you do the TCP connection handoff properly, the server can send the request response directly to the client. Okay? Otherwise, what will happen is the switch will send the request to the server. The server will send the response back to the switch because the request came from the switch, not the client. And the switch then sends it back to the client. Okay? Because the original request came from the client to the switch, and the switch then sends it back to the client. Okay? Otherwise, what will happen is the switch will send the request to the server. The server will send the response back to the switch. The switch then sends it back to the client. Okay? Because the original request came from the client to the switch, and then the switch sent another request to the server. Okay, so in this case, the switch is sitting in the response path, okay, which might slow things down. But if you do the right type of TCP tricks, you don't have to. You will see that the response went directly from the server to the client. That will only work if you actually do the right thing at the TCP level, which requires additional networking issues to be addressed. Yes, question.
So you said that there are some tricks that are useful. So can't we have another set of protocols for a distributed system which would take care of it? There is a load balancer which it comes to, and then directly this communication.
Yes, the question is, can there be another protocol where the request comes to the switch, but the response goes back from the server? That's your question, right? So HTTP does not support that, right? So the client is only talking HTTP. Here, what is happening? You sent your HTTP request to one machine with one IP address, which is the switch. The response came back from some other IP address. Okay? That clearly will not work because that's not how TCP works, right? So to make all that seamless to the client, you have to play some additional networking tricks at the server end so that when the response goes back, it looks like it actually came from the switch, because that's who you sent the request to, even though the response was handled by some other element. Okay? So again, this is not a networking class, so we don't need to get into how TCP connection handoff work. There's something called TCP splicing and so on. Okay, there are some details, I think, on the next slide. You don't need to worry about all of that as much. What you do need to worry about is essentially how does the load balancing. I think that's really more relevant from a web application standpoint. Do you do it at the request level? Do you do it at a session level? If there's caching, how do you deal with that? Because in reality, you will actually have a set of caches sitting between the switch and the real server. You look at the cache first. If there's the response is already in the cache, you will not even go to the server. Okay? So you'll put a cache sitting in between those two elements. So those are the more relevant issues for this class, but you will have to deal with some of those low-level things if you're building a large web application. Okay, does that answer your question? Okay, anything else here? All right. So with that in mind, let's actually think about how do you do load balancing. I already mentioned some of this. So you can do request-based scheduling, where the switch is forwarding each request to a replica based on some policy. Policy could be round robin, policy could be least loaded. Any policy you can think of, you can implement in the switch. Okay? So round robin and load-based policies are the most common. Okay? If you have state at the server, you should do the load balancing at a session level, not at the request level, because request will then of the session of the same session should go to the same replica. Okay? Again, you can use round robin or least loaded as your session-based policy. Okay? And I did mention a set of these networking techniques that are used by the switch to forward request to the right replica. Okay? There is something called HTTP redirect, which essentially allows you to forward at the HTTP level. Okay? The HTTP request comes in, the switch does HTTP redirect, it sends essentially the HTTP request to the right replica to handle. Or you can do TCP level redirect. So then the redirection is happening more at a transport level protocol as opposed to HTTP protocol. There are things like handoffs and splicing, which I talked about, but we don't want to get into it here. But those are techniques that are handled at the TCP level. Now, the switch may use either of these two techniques. It doesn't really matter, okay, but it has to essentially forward the request. And it will use one of these 2 or 3 techniques to forward requests. Okay. All right. So that's web clusters. But what I now want to talk about is a set of techniques these clusters can use to replicate the service as the load changes. Okay. So the reason you want to do all of this is to essentially deal with the dynamic nature of web workload. So if you have a large website, okay, the workload that it's seeing is not going to be static. It's going to keep varying by time of day, by the seasons, and so on. So for example, large e-commerce site naturally is going to see more workload during the day than night, because maybe people are asleep at night, not as many people are browsing. Okay. Also, if you have, let's say, a sale event, you might see more workload on those days than other days. So every time there's a long weekend, there's a sale. Right? There's a July 4th Independence Day sale, maybe there's Black Friday sales, and so on. E-commerce sites will start seeing a lot more workloads on those days than other days. Okay? So there will be variations at day scales, meaning at hour by hour. Okay, there's also variations by seasons, okay, whether there is essentially a long holiday and things of that. Okay, that's for shopping-based website. There's a different type of dynamics you'll see for other types of website, like news website. Okay? News website will see more traffic when there are big news events happening. If there's a big sporting event like the Olympics, there'll be more traffic, mostly to the sports section of that website, but there'll be more traffic. Okay? Or if some big news story breaks, there'll be certain surge in traffic on these news websites. Okay? So there are all kinds of dynamics that these web servers have to deal with. Okay? Now, if you have statically decided the size of your cluster, right? So in this case, for example, we had 4 replicas. Okay? You statically decided this server is going to be replicated 4 times. That gives that website certain capacity. Okay? But what if there is a surge of traffic that exceeds this capacity of those 4 servers? Okay? Then the server gets overloaded, right? Because there are more requests coming in that even 4 replicas cannot handle. Okay? Now, normally when there's an overload, then the website is simply going to take a very long time to respond to you. Okay? Or it might just return an error saying server busy or something like that. And you may have encountered this if you gone to some website that's statically provisioned where it got overloaded. Okay? Either it doesn't respond, okay, or it gives an error. Okay? This used to frequently happen for Spire during registration time. Okay? Everyone would try to register and the system would just not respond. And hopefully they solved that problem now, but that was a common problem. But many websites have this issue. Okay? So one thing that many of these more sophisticated websites do is to change the size of the web servers or the website rather based on load. Okay? Which means the number of replicas that you have in the system is changing over time. Just as if you remember in your thread pool model, okay, on a server, the number of threads was varying based on the load. Okay? Here you can vary the number of replicas itself based on load. This is referred to as elastic scaling. Okay? So elastic scaling basically means dynamically vary the capacity and the number of replicas of that website based on load. Okay? This is also known as auto scaling and dynamic provisioning. Okay? If you look at the really sophisticated websites, they'll all use elastic scaling because there is no really good way for them to know beforehand what is the maximum workload they're going to see. Right? That might change over time. And even if you're seeing some big, let's say last Black Friday, you saw a certain amount of traffic, there's no guarantee that this time that traffic won't go up. Maybe you are selling more popular items this time around. So you may vastly exceed what happened last time and so on. So elastic scaling is a way to deal with all of this. Okay? As the load goes up, you also dynamically create new replicas, okay, and provision. This can be only done in the cloud. Okay? The reason is in the cloud, you can go and ask for more servers on the fly, okay, and then add them to your replica pool. Okay? You can't normally do this. Well, you could if you have a cluster, but there are idle servers. But this is a popular approach in cloud where you can go and request more servers if the load goes above a certain threshold. You ask for more servers, you add them to the pool, and then your pool has become bigger. You can serve more work. Okay? So that's called elastic scaling. There are 2 approaches for elastic scaling. One is called horizontal scaling. The other is called vertical scaling. Okay? In vertical scaling, you don't actually increase the number of servers. You make the servers bigger by adding more cores and adding more memory. Okay? So think about you have a virtual machine or a container. Okay? The container or the VM gets overloaded. You can essentially add more CPU cores to that virtual machine on the fly. The hypervisor can just take unused cores on that machine and add them to the VM. The VM just got bigger. Okay? That is called vertical scaling. Okay? You're essentially making each of the replicas bigger in size by dynamically adding more memory or more cores. Again, this can be only done if your application is virtualized or containerized. If you just have a static website running on bare metal, you can't add cores to it. Okay? But you can do this if you have virtual servers. Okay? That is vertical scaling. Horizontal scaling means you can increase or decrease the number of replicas themselves. Okay? Here you can go ask for more containers or ask for more VMs from the cloud, you add them to them. Okay? So these are 2 popular techniques that are both used to implement elastic scaling. One is called horizontal scaling. You change the number of servers. Other is called vertical scaling, where you keep the number of servers the same, but you change the size of the servers. Okay? In both cases, you can change the capacity of the website, the web server on the fly. Is that clear? So that's elastic scaling. And there are multiple ways to actually implement elastic scaling. Your question, please.
Also account for web crawlers or malicious.
Okay, question is, does elastic scaling account for web crawlers or malicious users? So what you're asking is, web crawling can increase the load on a website. Okay, malicious users can just start sending a lot of requests, and that can also increase the load on website. Now, elastic scaling algorithm is not going to look at the cause of why the workload increased. Okay, it is observing the workload and simply taking action based on the workload. If you have to deal with malicious requests coming in, you need additional techniques to deal with. This will increase capacity, and it can keep increasing capacity, but maybe the malicious traffic also increases in proportion. It may not solve the problem, but you need other techniques to deal with security issues. Okay? So in this case, you are simply using simple rules, like you could say, whenever the workload exceeds 70% of utilization, add more replicas. It's simple rules like that. You can actually implement that rule on AWS cloud, for example. Okay? So it's not going to look at why the workload increased. Right? So in either case, you can implement elastic scaling more as a proactive measure or a reactive measure. Proactive measure essentially says you can look at the workload patterns. You can predict what the workload pattern might be in the near future and take an action before that. So if the workload pattern is going up, right, you can predict based on, you can do time series prediction. You can even use machine learning techniques to make predictions. You look at a sequence of load measures and say, what is the next load going to be? And then based on that forecasted load, then you can say, if the workload is going up further, let me provision the capacity before I hit that. Okay? That's called proactive. Okay? Reactive, as the name suggests, is actually reacting to real changes in the workload after they've occurred. Okay? So you track the workload went up, then you react to it and provision capacity. Okay? So proactive is trying to stay one step ahead by bringing capacity online before the site itself gets overloaded. Reactive is trying to react to workload changes as they happen. Okay? So you don't want the website to get overloaded even in reactive. So you can do that by keeping lower thresholds, saying if the workload hits 60% or 70%, add more servers. Don't wait for it to reach 99%, for example. Okay? So you can use reactive versus proactive scaling. So it gives you 4 dimensions, right? Are you doing things horizontally or vertical scaling? And is each of this being done in a proactive or reactive way? Okay? So you will see that all of these techniques are used by large websites like Netflix or Amazon's e-commerce website. They all will use some techniques like this to make sure the site always keeps running, regardless of how the workload fluctuations happen. Okay, yes, question. Yeah. Okay, question is, in vertical scaling, can you increase the number of cores or memory without restarting? Right? So if you have the right type of VMs, you can actually do that. Okay? So as an example, you can construct a virtual machine, say, with 10 cores. Okay? And you can map them. How the cores in the VMs are mapped to physical cores is actually independent. So you can have 10 virtual cores that are mapped to 2 physical cores. Okay? And so now if I add a third physical core, these 10 virtual cores are sharing 3 physical cores. So the VM does not actually see any difference. It just sees the same number of virtual cores, but the amount of physical resources you allocated has gone up. And they are being shared by the same amount of virtual resources. So no restarting is necessary. Having said that, there is a limit to vertical scaling. You can't vertical scale beyond the capacity of the physical machine. Right? So in horizontal scaling, you are limited by the number of machines you have. In vertical scaling, you are limited by the size of the machine. Right? So there is a little bit of a limitation there that horizontal scaling doesn't, I guess. Okay, question is what is happening in the real world? Is it common to do horizontal versus vertical? Both are in use, but horizontal scaling seems more popular than vertical scaling. It was easier to spin up replicas than what was just asked. Adding cores or memory in a transparent way is not easy. You have to set up your VMs the right way. Okay? But it's much easier to just start a new instance and add it to the pool. So then there is nothing to be done in that case. The load balancer does need to know there's a new instance and it rebalances the load and so on. But you don't need to know as far as the applications, VM is concerned, the OS is concerned. Okay. Got a question there somewhere? Okay. All right. Anything else? Okay. So that is elastic scaling. Let's talk a little bit about microservices and think about how to do elastic scaling in a microservices world. So you probably know now what microservices are because you implemented them in lab too. So it takes our multi-tier architecture, specifically the application tier, and breaks it down into smaller components. Okay? And so the idea is you have more modularity because rather than putting all your code at the application tier as the application complexity grows, why not partition it into smaller services? Each of the services exposes an interface. It could be an RPC interface, it could be a REST interface, and the services talk to one another. Okay? That's the basic idea. Okay? So this is essentially designed to overcome the problem of large monolithic architecture, or monoliths as it's called, where you have all of the code sitting in your application tier. Okay? So this is how lots of modern applications are built. Each microservice is small, and it can be implemented and maintained independently of others. You can upgrade the application by just replacing one microservice with a newer version of it. You don't have to bring the entire system down or anything like that, so long as that microservice interface hasn't changed significantly and it can continue to interact with other microservices. That's an easy way to implement new microservices, upgrade microservices, and so on. So both from a modularity perspective and a deployment perspective, microservices are essentially become very popular. Okay? But our goal is also to understand how it can be used to improve capacity. So now you can think about the elastic scaling problem that I talked about and apply it to microservices. Okay? So think about lots of requests are coming into a website. If you had a multi-tiered architecture, and not a microservice, with a multi-tier architecture, you would have to create replicas of that middle tier, which is where all the code is sitting. That's your application tier, and you'll replicate that. Okay? But maybe only some parts of that application are overloaded, not all of it. Okay? If you had same application written as a microservice architecture, you can look at which of my microservices are overloaded, and you can only replicate them rather than replicating everything. Right? This can be more efficient because you are only looking at which code is seeing the bottleneck and only replicating that code on the fly. And you can do horizontal or vertical scaling, so you don't have to replicate everything. In the multi-tier case, the entire middle tier is getting replicated, even though some parts of the code may not be that used by the requests that are coming in. So here you can independently scale independent microservices. Okay? So that brings us to essentially this picture, which shows us three ways you can implement scaling. Okay? Replication or horizontal scaling is actually just happens to be one of them. So there are three axes here. Okay? The first axis, y-axis, called functional decomposition. This says you can scale first by taking a big monolithic implementation and making microservices. That's a much more scalable deployment. So you are essentially doing what's called functional decomposition of your code and implementing microservices. So once you do that, okay, then the next level is what is called x-axis, is what is called horizontal scaling. You can independently take each of these microservices and scale them up or down as needed. Okay? That's essentially the x-axis. The z-axis is what is called data partitioning. Okay? This is largely used for the backend, okay? Because the backend is a database, remember. You can implement replication of that entire database, but that's going to mean that the database has to be kept consistent. Okay? Every transaction has to be sent to all the replicas because the state has to be kept consistent. That may not scale if every request that is coming in has to be processed by all the replicas. You're not partitioning a request. Okay? So the way you scale databases often is what is called data partitioning or sharding. Okay? You can take a big database and you can split it into smaller pieces, the data of the database. Right? Let's say, as an example, if you have lots of users in the system, you can say all users with last name starting from A to D, they are on one component of the database. All the users who have accounts starting from E to something else are on another replica, and so on and so forth. So now I've taken the tables of the database and I've split them. Okay? I'm not replicating the data, but I'm splitting the data. Okay? So now this will actually allow you to partition the workload, because as requests come in, those requests will go to one of the, they're not replicas, but they're different components of the database. Okay? This allows me to essentially split the workload. And I don't need to worry about consistency, because each component is handling requests for one user, as one example. Okay? So you can do this data partitioning in many different ways. For example, in your lab, let's say you have some number of items in the catalog, you could do the same thing. You could say all catalog items starting from A to D go here, and the next 30 go here, and the next go somewhere else. So then each database component is handling certain items, but not others. So you don't need to worry about replication and so on. Okay? So this is called data partitioning. It's another way to scale. Rather than replicating data, you partition data. Okay? So these are three common principles that many web application designers are going to use to scale their app. Okay? First is make microservices. Okay? Or now you can also do something called serverless, which does the same thing. You functionally decompose the application. Don't put all your code in one big application component. Split it into smaller components. Second is you then scale each component independently. Only the bottleneck components have to scale, the others don't have to scale. More efficient. Okay? And third is deal with data by not replicating data, but partitioning data. Okay? Which you can always replicate data, but partitioning also gets rid of this issue of consistency. So when you make copies, you've got to keep the copies consistent. That adds more overhead. Partitioning it actually solves some of that problem. Okay? So these are three dimensions of scaling. It's very popular in designing large-scale microservices and web applications. Any questions here? Okay, so those are all ideas for web application. Now we'll talk a little bit about HTTP and web documents and so on. Okay, so as you know, HTTP protocol essentially is a way of sending a request to a web server or a web service, and you can get back some response. And typically, the response is a document of some sort if your client is a web browser. The document can have different forms. You can have text documents, you can retrieve images, you can retrieve audio content from web servers, you can retrieve video content, you can receive PDF documents, you can also have what are called multi-part documents and so on. So these are all typical documents that an HTTP request from a web browser can retrieve for you. Okay? Now, regardless of what type of document it is, let's take a look at how HTTP actually works. Okay? So here's an example of a client making a request to the server. They will assume that client first makes a request, gets an HTML file. Okay? The HTML file has a set of images in it, embedded in. It has to then get each of these images from the server. Okay? So the browser can then make a request for each separate HTTP request for each of the embedded images and retrieve them. Okay? And that is what is shown here. You will see that there are three connections from the client to the server. Each connection is retrieving a separate request, a separate document. It could be an HTML document, embedded images, and so on. Okay? So plain HTTP protocol, which was version 1 of the protocol, that for every HTTP request, okay, from the client to the server, you set up a new HTTP connection. Okay? So you set up essentially create a new socket connection, send an HTTP request, get back a response, close the connection. You want to get more images from the same server, set up new socket connections, send more HTTP requests, get back responses. Okay? That was HTTP 1.0. So then this was called non-persistent HTTP, okay? HTTP 1.0. Then you had something called version 1.1 of HTTP, which is called persistent HTTP. Persistent HTTP as you see in this picture, there's one open socket connection between the client and the server. Okay, so you open one socket connection. Okay, you first send your HTTP request, get back your HTML page. Okay, then you parse it and see that there are some images. For those additional images, you will use that same socket connection and send another HTTP request. Okay, get back a response and so on. Okay, so now you are reusing the socket connection that's already established between the client and the server to essentially send multiple HTTP requests over them. Okay, one at a time. Okay, you have to still send them one at a time, but you can reuse that connection. Okay, this is going to reduce the overhead of establishing socket connection. Okay, because if you remember way back when we were talking about this, I said there's a three-way TCP handshake that you have to pay the cost. So if every HTTP request you have to pay it, there's a lot of overhead you are generating between the client and the server. You can save that overhead if you reuse the connection. Okay? But this brings some issues for you. So for example, what happens in this case is a browser, once you have made a, let's say, clicked on a link and gotten a page, okay, will keep that connection open to the server, thinking maybe you will click another link and go back to the same server, so you can reuse the connection. Okay? But how long should the browser wait and keep the connection open? Okay? Should it wait for 5 minutes? Should it wait for 30 minutes? Because you don't know when the user will click next. Right? So user might be reading something on the web page and may take 10 minutes and click a link, and then the connection is simply open and idle for that 10 minutes. Okay? Idle connection wastes resources on the server because you have all this TCP state you are keeping on the server. Okay? If you had closed that, then you would have released that and released those resources. But at the same time, you make frequent connections, also you waste overhead on the server, create more overhead on the server. So there is some balancing to be done when you have persistent HTTP. Okay? How long to keep the connection open after the last request has been seen determines the chances of reusing the connection, which is good, versus wasting resources on the server by keeping a connection idle because the user is not doing it, okay? Which is bad. So you don't know what the right answer is, but different browsers have used different policies on how long to keep it open and so on. Okay? So that's persistent HTTP, also called HTTP 1.1. Okay? It tries to improve what HTTP 1.0 did. Okay? Now, before we talk about version 2, here are some common methods that HTTP operations will perform. There are 4 main ones. Okay? There's the GET, which you should all be familiar with, and you did this for your lab, which basically asks the server to return a document that is essentially specified as a URL after the GET. Okay? Put is the opposite of GET. Okay? Put allows you to actually send content to the server rather than retrieve content from the server. Okay? Usually, most web servers are not going to allow you to send it arbitrary content through put. But there are servers that will allow you to upload documents. Okay? So those are going to be using put. So for example, if you want to upload a file to a website, that's what you will use to essentially upload a document. Okay? You can use post. This is often used to send forms. Okay? You fill a web form, you hit submit, so that content goes as a post request to the server. Okay? So post allows you to send information to the server, not documents, but send information to the server. Okay? And delete allows you to delete a document at the server. Again, most web servers are not going to allow you to delete arbitrary files that are stored on the server. But maybe if it's a storage server like Dropbox, you can use a website to delete a file that you yourself uploaded to the server. Or maybe it's Google Drive or something like that. If you're deleting, you can actually use the delete command in HTTP to do that. Okay? So variety of operations, 4 more key ones: get, put, post, and delete. There are some others, but we'll not talk about them today. Next time, I'm going to describe some other operations. Okay? But what we'll do instead is to talk about HTTP 2.0. That's essentially the newest version of HTTP that tries to overcome some problems that even 1.1 had. Okay? So 1.1 made HTTP connections persistent and tried to save overhead of creating lots of socket connections between the client and the server. Okay? But as it turns out, many servers actually don't use HTTP version 1.1 because even though you are reusing the socket connection, it is making the connection sequential. Okay? You send one request, you get a response. Then you ask for an image, from the server, you get a response. Then you ask for another image, you get a response. Okay, if there are 20 images embedded in the web page, you have to have 20 round trip times to get all of those images before you can display that to the user. Okay. In the meantime, your user has clicked on a link and is just waiting for the web page to load. Doesn't seem to be loading because you are making sequential connection. Okay. What many browsers do instead is they will use HTTP 1.0. After you get the first HTML page, they'll open multiple connections to the server and try to get all of the images in parallel, which is going to speed up your page load times. Right? Because if you get images in parallel, they load faster than you're getting them one at a time. Is that clear? Okay. So 1.1 didn't actually serve the purpose of reusing connection, because to speed up page load times, browser decided it's better to just open multiple connections anyway. Right? That's the only way I can do this in parallel, because 1.1 is strict pipelining. You have to wait for the previous request to finish before I can send the next request. Okay? So what do you think HTTP 2.0 did to address this problem? Okay, so you should be able to send concurrent outstanding requests. Right? So rather than have one request and wait for a response, can I keep sending requests without the previous response and have the responses come back, and I know which response is for which request? Okay? If you do this, then you solve the problem of HTTP 1.0. That is what HTTP 2.0 did. Okay? In addition to a few other things. Okay? It allows you to multiplex multiple connections in parallel over the same TCP connection. In this case, you don't need to open multiple socket connections, because I can send as many requests as I want over this one socket connections, even though responses have yet to come back. Okay? And when responses come back, they come with the index that tell you this response is for this outstanding request. Otherwise, you get a response, you don't know which request it was for multiple outstanding. So that solves the problem of persistent HTTP 1.1, because I can send multiple requests and get responses in parallel over the same connection. Okay? So no need to have multiple socket connections and no need to actually wait for requests. I can do parallel down. Okay? So in HTTP 2.0 lingo, these are called streams. Okay? Each request is essentially a stream that I've created, and I can have multiple streams multiplexed over the same TCP connection. Okay. HTTP 2.0 actually has bidirectional functionality, which I didn't talk about here, where the server can actually push data to clients even without client asking for it. Okay. HTTP is a pull-based protocol. Okay. You have to make a request before a response comes. In HTTP 2.0, you have push functionality in the HTTP protocol itself, where the server can actually push content to you even though you didn't ask for it. Okay. For example, if you had a cache, it's a good example. The browser has a cache, the web page changed, the server, if there's an active connection, can push the new version, so the cache gets updated. Okay. That's one example of why you would push content. Or you might be requesting, let's say, automatic updates. So you have weather widget, and every time the temperature changes, the server can push a new update to you rather than you polling the server. So all kinds of reasons you can have that essentially allows you to have bidirectional streams where server can push content as well. Okay? That's an additional thing that HTTP 1 or 1.1 didn't have. 2.0 actually had push functionality. But in addition, it uses compression. Okay? So you can compress the content before sending it, which means if you're on low bandwidth connection, or if you're on a cellular connection, which may not be as high bandwidth as, let's say, Wi-Fi, you can still get efficient use of your network bandwidth. Okay? So you can compress text files, you can compress all kinds of content before sending it. Okay? You can also use binary headers instead of text headers of HTTP. HTTP gets, as you know, you've done this using REST interfaces, they all use text interfaces. Okay? And text is not very efficient. You can essentially encode that in binary, and HTTP becomes more efficient. So it allows you to convert text to binary, it allows you to compress, and it allows all this kind of multiplexing to be done. Okay? So a lot of new innovations got added to HTTP 2.0, which most browsers now support. Okay? There are some other things that HTTP 2.0 did, which I'm not mentioning here. One of them was to run, rather than running over TCP, which is default for all of HTTP, you can also run over UDP. Okay? where you can get rid of the TCP connection over it. Okay? In fact, Google came up with a version of UDP called QUIC, QUIC, which is an acronym. I forgot what it means. So you can essentially run HTTP over QUIC, which makes it even faster. Okay? So essentially, if you have a Chrome browser connecting to Google servers, it actually uses QUIC rather than TCP connection, and then uses HTTP 2.0 on top of QUIC to get rid of many of these performance issues. Okay? So there's no connection establishment overhead if you use UDP. You got rid of the three-way handshake altogether. Okay? So a lot of new optimizations have been done. They are now being implemented further into a new version of HTTP that hasn't come out yet, but is under design. It's HTTP 3.0. Okay? If you go and Google HTTP 3.0, you will see what they are planning. But these are the kinds of things that are being done to improve HTTP performance. Okay? All right. So that's all I want to say about HTTP. Any questions? Yes, your question. Yeah. The question is, if you have push functionality, can it cause security issues where if you open a connection to the server can send malware to you, right? So that's true. I think the bidirectional functionality is actually used in very specific cases where the client consents to receiving updates from the server. It's not like for any arbitrary connection I open, suddenly the server is pushing content to me. That's not allowed. It has to be for, you have to, when you set up the HTTP connection itself, you have to specify that this is a bidirectional connection. The default one is going to be the standard one. The server can't push. But if the application already knows it wants to receive information from the server, you set up a bidirectional HTTP connection, which means that you know that the server here actually has information to push. Then that is only done for specific application. So you would say, if I'm connecting to a weather app, I will create a bidirectional connection. Then I can keep getting app updates and so on. Right? Notifications are another example. If I want to get notifications from the server, they all come as push. Right? So you can use things like HTTP 2.0 for that. You can use other techniques as well, but that's one way to do it. Right? So yes, you should not have browsers open bidirectional connection to arbitrary servers, because that will cause security problems. But these will be for specific applications. You will open that type of connection. Okay. Any other questions? All right, web services is the last thing I want to say, then we'll end here. So web services basically take this idea of clients and servers in the web world, but now have both the clients and server be two applications that are talking to one another, rather than a human with a browser talking to a web server. Okay? And you already know some of this because you implemented microservices. So in this case, you have two microservices talking to one another. Maybe the front end was talking to a catalog service. It was not a browser talking to the catalog service. So the catalog service is acting as a server. Its client is another service. It's not a browser. Okay? So how do these services talk to one another? So that brings us to this concept of web services, where now you have clients and servers as being two application components that interact. And then you're essentially talking over HTTP or other protocols. The original web service protocol used something called SOAP, okay? Simple Object Access Protocol, okay? For the two application components to talk to one another. SOAP was basically an RPC protocol. Okay? It used some web technologies, but at its heart, it was an RPC protocol. The way you wrote these web services was exactly the way you wrote an RPC-based application. You had to write an interface definition file. You had a special compiler that would generate the stub code. Okay? And then the stub code, you'll see the stub code being here. The stub code has to be compiled into the application. So for all practical purposes, this was another RPC system that used some web-based technologies. Okay? And the web-based technologies used was essentially the way RPC requests and responses came, they used XML. Okay? If you know what XML is, HTML has markup. XML is essentially a generalized version, which essentially uses a markup language. Okay? XML stands for Extended Markup Language. So here's a sample XML document. So you will essentially send requests as XML and get back responses as XML. Okay? That is basically what is being used to exchange information, and this is what basically was more compliant with the way web worked, because things are sent as HTML and whatnot. Okay? So this is an example of a XML-based SOAP language, and there is lots of header, but you will see basically it's making a call saying an alert call, and this is the argument you're sending over XML. Okay? It's pretty long amount of text that you say to make one RPC call and send one argument. You have to send all of that text over XML. Okay? So it was a heavyweight protocol. Okay? There's no question about it. And the SOAP never succeeded, okay? Because it was too complicated. It was much simpler to use standard RPC, or much simpler to just use HTTP and standard HTML and not think about using something in between that's half RPC but uses XML for data exchange. Okay? So what instead became successful was RESTful web services, which is basically a descendant of what started off as SOAP-based XML. And you probably know enough about this already. So SOAP used heavyweight protocols for distributed computing. REST uses HTTP. Okay? And rather than using XML to send data back and forth, it's just using HTTP requests and responses, which we already know how to use. You can just send GET request and get a response. That's your RPC call is the GET request, and the response to the HTTP request is the RPC response. Okay? Much simpler than sending some heavyweight SOAP documents and getting back responses and so on. Okay? So as I have said before, REST stands for Representative State Transfer. It's an acronym. Okay? And you're just using standard HTTP. If you say GET, that's a read. If you say POST, that's an update. You can also do a put to do a create or an update, to do a delete, to do a delete. So RESTful web services also a way to do RPCs. You are doing RPCs or HTTP now. XML, SOAP does not necessarily use HTTP. It can send XML or TCP or some other protocol. This is strictly HTTP-based RPC. Okay? So rather than using things like gRPC, you're using REST, you're essentially writing RPC that goes over HTTP. Much closer to what we already know. Here's an example. Okay? So if you want to get a stock price of some company, you send a GET request, you send the function name and then the argument, which is a part of that URL. Okay? And then the response comes back as an HTTP response. Okay? If you had an XML response, that is what it would look like. Okay? But if you send HTTP response, that's what it looks like. But you can also get a JSON object back, as you know. Okay? You don't have the responses, don't have to be text. They can be JSON object. They could also be XML in some cases. Okay? But it's still coming as part of an HTTP response. Okay? Here's that same call if you had written that application using standard web services and SOAP. Okay? That entire text there is just saying, give me the stock price of a company. There's a big header, there's a big body, everything has XML encapsulation, and this is what the response looks like. The only thing important here is that number, which is the actual stock price, but there's a lot of extra overhead into making it a XML-based document. Okay? And because the overheads were high and it was slow, never really took off. Okay? What became popular instead is just do everything as HTTP requests and responses. Okay? And we'll just use that as a way to send RPC messages and get back responses. Okay? So I'm going to stop here with this one last slide, which is comparing SOAP and RESTful web services. Okay? The left column here is all properties of standard web services and SOAP. Here is what RPCs do. Okay? So this one is language agnostic, platform agnostic, transport agnostic. Okay? Here the transport is HTTP. You can't change that. Okay? But you can write your RESTful web application in any language you want and any platform you want. Okay? That's not restricted. So you still have a lot of flexibility. Okay? This is designed to support general purpose distributed computing. Okay? Multiple components all talking to one another. Here it's point to point. Okay? One web microservice talks to another microservice using a single HTTP. You can also talk to others, but those are separate messages. Okay? So it's point to point RPC calls. Here you can do more sophisticated calls. This uses a bunch of standards, web service definition language and all kinds of things. Never really became popular. There is no real standard here other than say use HTTP. Okay? You can then, as I said, you can send back your responses as JSON. You can send back as XML and send back as text. Okay? That's up to application designer. Okay? The RESTful web services does not say you have to send back responses in a certain way. If you did SOAP, you have to, everything is XML. You can't change it. Here you can decide. So long as everything runs over HTTP, you get to decide what to do. Okay? So this has built-in error handling. It was extensible, quite heavyweight. Here things are much simpler. Okay? Tied to HTTP transport layer, much more efficient. Okay? Yes, question.
How SOAP is distributed? How is it used and distributed, and why REST cannot?
Okay. Question is, how is SOAP distributed and why REST cannot be distributed? So what I should have probably clarified is you can actually send SOAP requests to multiple entities at once. Okay? You can have one entity take that request and make additional calls. All kinds of complex scenarios are possible using SOAP. Okay? When you are doing REST-based applications, you make a HTTP request, it goes to one component, you get back a response. Now that component can make other requests. That's a separate call, right? You are not trying to have one call do complicated thing. Here you could do that just as you could have an arbitrary distributed application with multiple components that are interacting with one another. That was the model they had in mind. Here is used assumes client server. Okay? There are two entities talking to one another over REST, and those entities can talk to other entities also, but that's separate REST calls. Okay? So much cleaner point to point. All right? Yes. Okay. The question is, can HTTP 2.0 makes microservices vulnerable because of push function? Okay, so as I had said previously, the push functionality is only used in specific cases. It does not have to be enabled for every HTTP request. The standard HTTP 2.0 request will not accept push. You can only make requests and get responses. There's no concept of push. You will never accept push requests. If you want to get push messages, you have to open a certain type of an HTTP 2.0 connection, which is called a bidirectional stream. If you say, here's a HTTP connection and this is a bidirectional stream, you are explicitly expecting the server to push messages. Right? So it is not the case that any HTTP 2.0 connection will mean the server can push to you, because you will open a unidirectional stream, which means the server can't automatically push content. So then that problem goes away even if you're running RESTful web services on HTTP 2.0. Okay. Any other questions here? Okay, so we will end it 10 minutes early and then we'll resume on Wednesday. Okay.